Hello, AP Chemistry. This is Mr. Coker. Welcome back to second semester. This is going to be Chapter 11, Properties of Solutions. In the Zumdahl book, 10th edition, it's pages 433 through 464. So I'd suggest read the textbook, watch this video, and then in class we can work on problems and questions you have for me on this topic. Properties of solutions. Remember chapter 10, we just covered liquids and solids. So solutions would be mixtures, so not pure substances. We'll start out talking about solution composition. When a solution has a high composition of solute, we say that it's concentrated. When it has a low concentration of solute, we say it is dilute. Concentrated and dilute. There are many different ways to express concentration. Molarity is one way, and that is typically the chemist's way, especially if you're going to do any stoichiometry, because it gives an easy way of calculating moles. Molarity is when you divide the moles of solute by the total liters of solution. Moles of solute over liters of solution. By multiplying molarity times liters, you can get moles. And that is a quick way of finding moles in order to do a stoichiometry problem. There's also mass percent. This would typically be how you would buy things in the store. Say you were buying some bleach or some peroxide or some other solution. You would typically do some kind of percent, mass percent, maybe volume percent, something like that. It's mass of solute divided by mass of solution. That ratio times 100% gives you the mass percent. Don't forget the bottom is mass of solution. It's not a ratio of solute to solvent. It's a solute to solution ratio. Another way that's a little more chemical would be to do a mole fraction. A mole fraction is, the symbol for that is this capital X, or sometimes a Greek letter chi. The mole fraction of component A, which could be the solute or the solvent. The mole fraction of component A is the moles of A divided by the total moles of all of the components in the solution. So if you say you had a two-part solution, you have 2 moles of A and 3 moles of B, then you would have 2/5 would be your mole fraction. Mole fractions, I know this sounds weird, but typically are represented as a decimal. Not as a percent, not as a fraction of a number over another number, but really typically it's represented as a decimal. So a mole fraction of 2/5 would be called 0.4. You'd say the mole fraction is 0.4. Molality. This is typically used for boiling point elevation and freezing point depression problems, which we will get to later in this topic today. Molality, typically with a lowercase m, capital M is molarity, lowercase m molality, is moles of solute per kilograms of solvent. So it's based on the mass of the solvent and the moles of the solute. Now, mass percent, mole fraction, and molality, if you know what you're doing with converting units between grams and moles and so forth, you can actually interconvert between mass percent, mole fraction, and molality, assuming you know the molar mass of each of the components. However, to convert to molarity or to convert molarity to these other units, you must also know the density, because the density is needed to find the liters of solution. One final solution composition unit is normality. Normality is the moles of equivalence over liters of solution. With normality, you multiply the molarity by an integer based on the number of equivalents of that chemical. For example, the number of H pluses that an acid might bring to a solution, or the number of electrons needed for an oxidation reaction. So these are typically, normalities are typically used for acid-base or redox reactions, or even titration problems. An example of a normality would be if you had 1.5 molar H2SO4, Since H2SO4 has 2 protons and neutralizes twice as much base as HCl, 1.5 molar H2SO4 would be called 3.0 normal H2SO4 because of its double power to neutralize base. Now, normality is not used on the AP test, and I'll tell you, it's kind of going out of fashion in chemistry. It's not even used that much in chemistry courses in college. We're kind of just covering all the bases by including normality here, but typically on the AP test, they expect that you will use molarity and then the mole ratios from the balanced equation to solve the problems and not to convert things to normality. So, best to stay away from normality. Check out examples 11.1, 11.2 in the book to practice the math on molarity, mass percent, mole fraction, molality, and normality. Keep in mind, solutions are not just things dissolved in water. You can have gases dissolved in gas, such as oxygen dissolved in nitrogen to make air. Some examples of various mixtures that really are considered solutions. All you really need to have a solution is a homogeneous mixture, and it can be various states of matter. Okay, moving on. 11.2, the energies of solution formation. We break the formation of a solution down into 3 steps. Think of this like Hess's law, when you can do things in multiple steps and then put it back together to get the total reaction. So we think of dissolving. Dissolving means that the solute particles are going to separate apart from each other. Salt is going to break up into ions. Sugar is going to break up into molecules. The solute particles are held together by some kind of attractions, ionic or intermolecular forces. Those forces are going to be broken, and you're going to spread the solute out. Step 2, you also need to spread out the solvent particles, which also typically will involve some kind of breaking of attractive forces if it's a liquid or a solid. The separating of the solvent particles is step 2. Finally, in step 3, you're going to reform some bonds or some intermolecular forces between the solute and the solvent particles. You're going to recreate some bonds. You've broken bonds to expand the solute. You've broken bonds to expand the solvent. See the diagram below. To form the solution, you're going to regenerate some bonds, but these bonds are going to be solute-solvent attractive forces. So step 1 and step 2 involve breaking bonds, or in the case of, say, water, intermolecular forces. So step 1 and step 2, those are endothermic. Step 3 forms bonds, so it is exothermic. So delta H1, breaking the bonds in the solute, delta H2, breaking the bonds in the solvent, plus delta H3, breaking the bonds in the reforming bonds between the solute and solvent. Those add together to get the delta H solution. Remember, delta H1 and delta H2, those are probably going to be positive numbers because you're breaking bonds. Delta H3 is going to be negative, so depending on the relative sizes of delta H1, delta H2, and delta H3, the delta H solution can be positive or negative. Now, if we think about how this impacts the ability of certain solutions to form, let's analyze the solubility of oil in water. Oil, being a solute, would have some intermolecular forces, but probably quite weak. So delta H1 is going to be positive, but fairly small. The second step would be breaking the bonds between water molecules. Well, those are hydrogen bonds, and those are fairly strong, so delta H2 is positive, but it tends to be larger. Now, let's put them together and create bonds between the water and the oil particles, the oil molecules. Now, this is an dipole-induced dipole force, which is not as strong as, say, a hydrogen bond. So delta H3, despite being negative, is going to be fairly small. So you've got 2 positive numbers, one small and one large, and then you've got a negative number, which is kind of small. So when you typically add these together, to form a solution between oil and water, it's going to be fairly endothermic. A delta H solution is going to be fairly large and positive, mainly due to the large positive hydrogen bond breaking that you had to do to expand the solvent water. As a result, we typically say that oil and water have a hard time forming a solution because it's so endothermic. It just takes so much energy to make that solution that at room temperature or at low temperatures or normal temperatures, say 0 to 100 degrees Celsius, the liquid state of water, you're not going to see much oil dissolving in water. It's just too endothermic. Now, on the other hand, if we look at the solubility of salt in water, the solute has fairly large lattice energy to expand the solute. In the case of salt, that's about 786 kilojoules per mole. You also have to break the water molecules apart. However, breaking the water molecules apart combined with forming the ion dipole forces is about 783 kilojoules per mole exothermic. We say that is the heat of hydration. So the forming of the sphere of water molecules around the sodium and chloride ions. So when you put the two together, kind of delta H2 and delta H3 together are about negative 783 kilojoules per mole. You put that together with the delta H1, which is positive 786, the heated solution for salt is only about plus 3 kilojoules per mole. Now, once again, that is endothermic, but just very slightly endothermic. So what is it that drives the formation of dissolving salt in water? Because we know salt dissolves easily in water. Well, the thing that drives it here is actually the chaos or the entropy of forming the solution. A solution of salt in water is much more disordered than the salt in a crystal. As a result, this increase of entropy actually is going to drive the formation of the solution and make it favorable. We will talk a lot more about entropy and the importance of entropy combined with enthalpy to generate favorability in formation of physical and chemical changes. But in this case, we actually blame the formation of the solution on the entropy change because the enthalpy change is actually almost zero. Considering energy terms, you can actually predict which kind of combinations are favorable. You can see down below that on the right bottom here that their energy terms for various types of solutes and solvents are looked at, and I would highly suggest going through each example, looking at the delta H1, the delta H2, and the delta H3. Keeping in mind delta H3 is a negative number, delta H1 and 2 are positive numbers. Similar to solution formation, you can also look at the interaction of solute and solvent particles when you're looking at chromatography. Paper chromatography, thin layer chromatography. These are when dyes are going to move typically up a stationary phase carried by a mobile phase, and what you're looking for chromatography is for one of the dyes to move at a different rate than the other, so you get a separation. Typically, if your dye is more attracted to the mobile phase, in other words, forms stronger molecular interactions, or we could say is similar in polarity to the mobile phase, then your dye is going to move up the paper, up the thin layer chromatography strip. If the dye is more attracted to the stationary phase, it's going to latch on to that stationary phase and not be moved up the paper or the thin layer chromatography strip. And you're going to get the dye separating that way depending on which ones are more attracted to the mobile phase, which ones are more attracted to the stationary phase. Generally, you can assume that it will be more attracted to the one which it has more similar polarity to. Now, what are some factors that affect solubility? So typically we see in solutions that solubility can be limited in many cases to a particular number. So what are the factors that affect whether A dissolves in B or not, and whether it dissolves well? Well, let's look first at some structure effects, polarity and shapes of molecules, and the ability to form intermolecular forces. A solution is favored when solutes and solvents have similar polarities. We saw that back in 11.2. An excellent example of this is the dissolving of vitamins in the body, either in the water portion of the body or the fat portion of the body. The fat in our body is nonpolar. The water in our body is polar. There are actually 4 kinds of vitamins that are nonpolar or hydrophobic and do not like to dissolve in water but will dissolve in fat, and those are A, D, E, and K. Those vitamins are actually dangerous to megadose, because if you megadose, in other words, you decide to take supplements of A, D, E, and K that have high concentrations of A, D, and K in them, you actually can cause A, D, E, and K vitamins to build up in the fat in your body. They're not flushed out by urine because they're not water soluble. So they come into the body uses them, but if they don't use all of them, the rest is stored in the fat. You can actually build up to such a level in the fat of your body that you can get hypervitamintosis. So this is not seen, however, with C and B complex vitamins. Looking at the structures down below in the lower left-hand corner, C and B are more polar and can hydrogen bond with water, so they are hydrophilic. They're more soluble in water. As a result, some people do megadose on C and B. Linus Pauling suggested for health effects that megadosing on vitamin C was actually beneficial. Well, megadosing is, although different scientists disagree on just how beneficial megadosing on C and B are, it is safer than megadosing on the hydrophobic vitamins. And that is because if you take excess amounts of vitamin C and B into your body can flush it out with urine because it is water soluble. Another factor affecting solubility is pressure effects. This effect really only applies with gases dissolving in liquids. Henry's law is the law that describes how pressure effects of gases in liquids is able to affect the solubility. It says that increasing the pressure of a gas over a liquid increases the solubility. Basically, you're like forcing the gas molecules into the liquid phase by making them more concentrated in the gas phase. So by having more in the gas phase, you see that the opportunities to dissolve in the liquid phase are actually increased. So in the middle here, down below, we see an illustration of Henry's law. This is used in carbonating sodas. Notice when you open a soda, the gas pressure is released. That is because it was bottled or canned at a high pressure in order to get more carbon dioxide to dissolve. It's actually a linear relationship, that the concentration of gas dissolved in a liquid is some constant, or Henry's law constant, that varies from gas to gas and liquid to liquid. But you have a constant that it depends on the gas and the liquid times the pressure. So doubling the pressure of the gas actually doubles the concentration in the liquid that will dissolve. Now it has to be the pressure of that particular gas, not just the pressure of all the gases over the liquids. It is the pressure of a particular gas affects the concentration of that gas. So you break the gases up individually if you have multiple gases. Henry's law does not apply well when gases ionize in water, for example HCl, because you now no longer have an equilibrium between HCl gas molecules in the gas phase and HCl gas molecules in the liquid phase. The HCl in the liquid phase actually split into H plus and Cl minus. So you can actually get quite a bit more HCl dissolved in water, and you can get up to a 12 molar HCl solution for concentrated hydrochloric, simply because HCl ionizes into H plus and Cl minus in water. So you would not expect HCl to obey Henry's law specifically. Interactive examples 11.4 is about Henry's law. Now the last one is temperature effects. In most cases, most solids are going to dissolve better in liquids than at higher temperatures. So higher temperatures typically allow them to dissolve better. Now remember, this is not that they dissolve faster. Solids dissolve more rapidly at higher temperatures regardless of whether they dissolve better or not. They'll still dissolve more rapidly. But dissolving at a higher solubility level depends on temperature, and as you see by the graph down below, that solids tend to have a positive slope to their solubility curves. They dissolve better at higher temperatures. And you can go back to looking at the previous section on endothermic and exothermic solutions. Solids tend to be endothermic solutions because of the high amount of energy it takes to break the bonds in the solid to create an expanded solute. As a result, these positive slope solubility curves are typically seen when you have endothermic solutions like solids. Gases, which really have no attractive forces in the solute state, but do have attractive forces between the liquid and the gas. For example, water and the gas will form a dipole-induced dipole attractive force. Those tend to be less soluble at higher temperatures because you are supplying the energy needed for the endothermic process of breaking apart the solution. This means that putting heat into water, such as a power plant next to a river or lake, like Clinton Power Plant, Clinton Lake, this can actually create thermal pollution in the water. Just the pollution of adding heat to the water can lower your oxygen, your carbon dioxide, and your other gases concentration in that natural water source. And that can affect plant life and fish life in the water. If you accidentally turn up the heater on your aquarium too high, thinking you're going to save your fish in the winter in a cold house by raising the temperature of the water in the aquarium, you're actually going to kill your fish probably because you're going to suffocate them because the solubility of the gas oxygen decreases with higher temperature. The book also gets into how boiler scale forms, which we will actually address in more detail in chapter 14, but I do suggest you look at how they talk about how the decrease of solubility of carbon dioxide can lead to boiler scale if your solution has calcium ions in it. 11.4 talks about the vapor pressure of solutions. We've seen that solutes can affect the physical properties of solvents. For example, antifreeze is dissolved ethylene glycol in water, and it raises the boiling point and it lowers the freezing point of water in a car's cooling system. Salt added to water lowers the freezing point, and as a result, putting salt on the road in the wintertime can melt the ice by lowering the freezing point, not by generating heat. By lowering the freezing point, you melt the ice. You bring the temperature of the freezing point below the air temperature, and that allows it to melt the ice. If we start with simple, we would start with a non-volatile solute, which will lower vapor pressure of a liquid because it will block the escape of some of the liquid particles that are trying to escape to the vapor phase. In the upper left and the bottom here where we've got our four diagrams, you see the red and black particles. The black particles are solute particles. They are non-volatile. They do not escape to the vapor phase. Only the red solvent particles can escape to the vapor phase, but the black solute particles at the surface of the liquid will block the attempted escape of some of the solvent particles. As a result, fewer particles escape to the vapor phase. The black solute particles do not block the return of vapor phase particles to the liquid, and so as a result, your condensing or the condensing, the returning of the liquid to the liquid phase of the gas particles, vapor particles, above the liquid is not slowed, but the evaporation is slowed, and so your new equilibrium vapor pressure is actually going to be lowered. So we say that the vapor pressure is lowered by the solute particles. Raoult's law actually is the equation for vapor pressure and concentration. It says that the pressure of a solution, the vapor pressure of a solution, will be the mole fraction of the solvent. Let's say that the solvent represents 80% of the particles, so then that would be 0.8 times the vapor pressure of the pure solvent. So if your pure solvent has a vapor pressure of 100 millimeters mercury and you have a 0.8 mole fraction of your solvent, you'll only have 80 millimeters of mercury for the vapor pressure of the solution. Calculations practicing that are in interactive example 11.5. Vapor pressure can then be used if you wanted to say find the concentration of solute particles in a solution. So that's one way of finding concentration, is by measuring vapor pressure and comparing the vapor pressure of the solution to the vapor pressure of the solvent. We see when we do this, for example, that sodium chloride actually gives double the amount of vapor pressure lowering you'd expect for salt. For example, per mole of salt and mole of sugar, you'll get double the effect. And that is because in water, salt is not just NaCl, it's Na plus and Cl minus. It splits into two particles. By dissociating into two ions, you actually get double the number of solute particles per mole of salt. It's one reason why salt is used on the roads, because you get double the effect. Non-ideal solutions are generated when you don't have even solute-solvent interaction compared to an average of, say, the solute-solvent-solvent-solvent interaction. You have particularly strong solute-solvent interactions, for example, acetone and water. The double bonded O for the acetone and the water are able to form hydrogen bonds. So as a result, since acetone can't form hydrogen bonds with itself, acetone and water have particularly strong solute-solvent interactions. And this will actually lower the vapor pressure because it will make it more difficult for the liquids to escape to the vapor phase. We say this is negative deviation from Raoult's law. If you have uncommonly weak interactions, such as ethanol and hexane, ethanol can hydrogen bond to ethanol, but it can't hydrogen bond to hexane. So the solution has weaker intermolecular forces than the average of, say, the two pure liquids. This will give a positive deviation. In other words, it'll be easier for the ethanol and the hexane to escape to the vapor phase than the average of the ethanol and the hexane in pure form. The interactions of solutes and solvents are also related to endothermic and exothermic character of solutions. For example, if you have an endothermic solution, it has particularly strong bonds in the pure form and weaker bonds in the mixture form. So as a result, that would give a positive deviation. So a positive delta H actually gives a positive deviation from Raoult's law. A negative delta H, or an exothermic solution, should give a negative deviation to Raoult's law. It's a general rule. Now, I've slipped into talking, I actually have stopped talking here about non-volatile solutes. If we talk about acetone and water, or ethanol and hexane, we're actually talking about two volatile liquids. Two volatile liquids will actually have a vapor pressure which will be the sum of the vapor pressure of the first and the second component of the liquid. They're both able to escape to the vapor phase, so Dalton's law says that the pressure will be the pressure of one gas and the pressure of the other gas. Down below in the yellow and green and black diagram there down below, we see the vapor pressure as a function of mole fraction for the pure liquids and the combined two liquids into a solution mixture. If we start with the dotted green lines, the dotted green lines are actually a graph of what vapor pressure you would expect for each liquid by itself, P1 and P2. So starting with the, for 1, when the mole fraction is 0 on the far left, you would expect no vapor pressure above the liquid because you have none in the liquid to evaporate. If the mole fraction of P1 is 0, the mole fraction of P2 will be 1, and so P2 will actually have the greatest amount of vapor pressure it can have at that particular state. So it will have its full vapor pressure of the pure liquid. Now we would expect these to rise and lower linearly with a positive and negative linear slope as you increase the mole fraction of the first one and decrease the mole fraction of the second one. That would be illustrated by Raoult's law. The mole fraction is the x-axis, and the pressure of the solution is the y-axis, and P naught of the solvent is our constant. So we think of y equals kx. P naught of the solvent is your constant times the mole fraction x, which is changing linearly or changing consistently, so the pressure of the solution should be going up or down depending on whether the mole fraction is increasing or decreasing linearly. Now, if we take the two dotted lines for P1 and P2 and add them together, you get the dotted line across the top. That dotted line is the combined vapor pressures of P1 and P2, or the vapor pressure of the solution. Now, on the left we see what happens if you have positive deviation. If you have positive deviation, the graphs, instead of being those three dotted green lines, become those black lines with higher vapor pressure than expected. And then on the right we see a negative deviation, so that the real is lower than the ideal. If you wanted to do Raoult's law for two liquids that are both volatile, what you would use is P total equals XA PA, or mole fraction of A, times the vapor pressure of pure A, plus mole fraction of B times vapor pressure of pure B. That's actually kind of combining Raoult's law with Dalton's law of partial pressures. Interactive example 11.7 talks about a mixture of two volatile liquids. Now you're wondering probably, what's this bell jar over two beakers of water here in the middle? It's actually showing the tendency of water to leave a beaker of pure water and transfer to a beaker of solute dissolved in water. Because the water vapor pressure is greater over the pure beaker, water will actually leave the water side faster than it comes back, and it will actually join the solution faster than it leaves. So in fact, over a period of time, you could actually see a beaker of, say, concentrated salt water and a beaker of pure water that put a bell jar over it, and in fact what will happen is the water will go down and the salt water will go up in volume. So think about what's happening at the molecule level and the tendency of the two liquids to evaporate and how that actually can occur. The graph on the right is for when you have solvent A and the mole fraction of A goes up, the vapor pressure goes up. And so we have on the right with the black and the red what would be a non-volatile solute, and then we have in the yellow, green, and black in the lower left what would be two volatile liquids dissolved together. Okay, 11.5. So if we know that solutes affect the property of vapor pressure, we can actually predict that it would also affect some other properties. For example, freezing point depression, boiling point elevation, osmotic pressure. These are all examples of colligative properties which depend on the number of solute particles. In fact, they have direct relationship to the number of solute particles. They even can be used to find concentration of solutes, these three colligative properties. Now, the Van't Hoff factor is what we add to the equation if it's an electrolyte dissolved in a solution and it splits into multiple particles. For example, for salt, we would have a Van't Hoff factor of 2 because NaCl splits into Na plus and Cl minus. If we look first at boiling point elevation, it doesn't take a lot of imagination to see that adding a solute would affect boiling point, because if you remember, boiling is when your vapor pressure equals your atmospheric pressure. If you lower the vapor pressure by adding a non-volatile solute, you're going to take a liquid that maybe is hot enough to boil, and now it's no longer hot enough to boil because you've lowered its vapor pressure. It's no longer equal to atmospheric pressure. So adding salt to boiling water would actually stop the boiling because it would lower the vapor pressure. However, if you continue to add heat, you can actually bring it back up to a boiling phase or boiling temperature. By elevating the boiling point, you can get it to boil at a higher temperature. The equation for boiling point elevation is the change in the boiling point, delta T sub B, is equal to the molal boiling point constant. Now in the case of water, that's 0.51 degrees Celsius per molal, times the molality of the solution, lowercase m, times your Van't Hoff factor, which may be 1 if you have a non-electrolyte, or 2 or 3 or 4 if you have an electrolyte that splits into multiple particles. Now we also see freezing point depression. This one's a little bit tougher to explain because usually we don't think about freezing, which is between a liquid and a solid, being related to vapor pressure. However, if you think about what's happening at the particle level, in a pure solvent, such as pure water, picture in the bottom right, the water can escape from the solid phase, and the water can join the solid phase. It can, in other words, it can melt and it can freeze at the same rate if you're at the freezing point. So at the freezing point, you have melting and freezing being equally favored. They can escape and refreeze at the same rate. However, if you add a solute, remember the solute is only going to be in the liquid phase. It's not going to be in the solid phase. There is no salt in frozen salt water. Frozen salt water freezes out the salt, and only pure water freezes in the crystal. The salt does not fit the crystal pattern of water. As a result, the solute is only seen in the liquid phase. Now, in the liquid phase, it does not block the solid from melting, but it will get in the way of some liquids particles trying to freeze. So by making it harder to freeze and not affecting the rate of melting, it will actually mean that you have to get it even colder to freeze. So important to remember that adding a solute raises the boiling point but lowers the freezing point. Now this is easily identified if you look at the vapor pressure curve on a phase diagram. Remember these 3-region phase diagrams with the solids on the left and the liquids in the middle and the gases on the bottom right. By lowering the vapor pressure, you actually get this blue curve, which means that you end up lowering the freezing point on the left, number 4 compared to number 2. You lower the freezing point, delta TF equal KF times M times I, but you raise the boiling point, delta TB equals KB times M times I. Another effect that is a colligative property is osmotic pressure. Now, you probably have a fairly extensive understanding of osmosis from biology, but let's review it one more time. The semi-permeable membrane allows solvent to go through, but will not allow solute to flow through. So in the U tube down below, we see that it is easier for solvent to travel from left to right than to travel from right to left. The solute particles are blocking the movement of the solvent through the semi-permeable holes in the membrane, but the solute particles do not block the solvent from traveling through from the other direction. That's because the solute's on the right. As a result, solvent travels left to right more than it travels right to left, and solvent builds up on the right and leaves the left side. This will actually cause a change in the height of the liquid on the left and right side of the U-tube and generate some pressure. And once you get enough pressure, hydrostatic pressure on the right side, it will actually stop the flow in the direction from left to right. That pressure is symbolized as pi osmotic pressure, and it's equal to the Van't Hoff factor, I times molarity times the gas constant R times the temperature in Kelvin. Pi equals IMRT. Osmosis can have some effects when we look at the blood. This is why you always try to give IVs or intravenous fluids that are isotonic to blood. You think of an IV being a saline solution, it's a salt solution in order to be isotonic with blood. If it's isotonic with blood, when you put it in the bloodstream, it's not going to cause water to travel in or out of the cell membrane. The cell membrane is a semi-permeable membrane. It allows water to pass through. If you have, say, a hypertonic solution, which is more concentrated than the ion solution that is inside the cell, you'll actually see that the water will travel out of the cell will shrivel up, and that's called crenation. If you were, say, to put pure water into an IV and then put it into a person's body, what will actually happen is the water will travel from outside the cell, which has a low concentration, to inside the cell where the solute has a higher concentration, but the water has a lower concentration. So water is actually going to flow to where it has a lower concentration. It's going to flow into the cell. As a result, the cell will swell up and in fact can burst, which is called hemolysis. So you have hemolysis and crenation, which are two negative effects that can occur to blood cells if you don't match the IV tonicity with the blood tonicity. Dialysis is similar to osmosis, but with dialysis, your dialysis tubing actually allows not just water to pass through or solvent to pass through, but also solute particles. So with dialysis, you actually pass the blood through the dialysis tubing, but outside the dialysis tubing, you have a dialyzing solution that has similar concentration of water and solute in it. It just doesn't contain the contaminants. So as a result, the contaminants are going to leave this through the dialysis membrane at a faster rate than they return, and that will slowly and effectively clean the blood. Interactive examples 1111, 1112 are going to talk about osmosis and dialysis. There's also the process called reverse osmosis. So instead of allowing osmosis to build up pressure, you actually counteract that pressure with even more pressure from on the side where the contaminated or water with solutes are. As a result, you end up forcing water back to the side with the lower concentration of solutes. And in fact, what you're effectively doing there is you're filtering the water by forcing it through the membrane in the opposite direction that it would naturally want to flow, just by putting the other side under pressure. This ends up allowing you to collect fresher water or fresh water, and you can even use this for desalination of seawater just by using pressure to force the water through the dialysis tubing. There's a diagram in the lower right-hand side of how reverse osmosis works. Okay, 11.7, just to review, as we mentioned earlier, electrolyte solutions are solutions that have solutes that split into separate particles. For example, HCl is an electrolyte because HCl breaks into H plus and Cl minus. NaCl breaks into Na plus and Cl minus. Calcium chloride breaks into calcium plus 2 and 2 chlorides. We call those processes ionization or dissociation, depending on whether you start with a molecule or an ionic compound. So those kinds of electrolytes are going to need an extra multiplier called the Van't Hoff factor, I. I is defined to be the moles of solute particles divided by the moles of solute dissolved. Now ideally we expect the Van't Hoff factor to be a 2 or a 3 because we expect full dissociation or ionization. In reality, there is an effect called ion pairing. This is seen more extensively in concentrated solutions. Ion pairing can basically take two ions and make them only one particle. As a result, you get a diminished effect. Instead of your I being, for example, in a 0.05 molal solution in the blue table, for salt you expect I to be 2.0. The observed I value is only 1.9 because of some ion pairing. You don't get as many particles as you might expect. You can see what the ion pairing is greater when you have particles that have higher ionic charge and smaller size. In other words, if the particles of ions, if the ions are more attracted to each other, they're more likely to do the ion pairing. So you see actually a very large effect for magnesium sulfate, MgSO4. And that's because Mg plus 2 and SO4 minus 2 have charges of 2 and 2, so your Coulombic attraction is 4 times greater than for NaCl, which is plus 1 minus 1. So with greater Coulombic attraction between the ions, they're more likely to do the ion pairing. And the more they do the ionic pairing, the less we see the Van't Hoff factor taking effect to its ideal value. Let's wrap up with colloids. Now colloids are sort of like solutions in that they stay mixed, but true solutions are considered homogeneous and have solute particles smaller than 1 nanometer. In colloids, you can get up to 1,000 nanometer particles in size to remain dispersed in a liquid or a gas or whatever dispersing medium, simply due to collisions with those solvent particles and electrostatic repulsion between colloidal particles preventing coagulation of those colloidal particles. Now you can actually reverse the process and get coagulation to occur by heating or maybe adding an electrolyte like salt to a colloid. You can actually get them to coagulate and form larger and larger particles and separate out, and they'll become suspensions and settle out. We see this with colloidal-sized clay particles in the soil that get washed into rivers, creeks and streams and rivers. We see this, say, at the mouth of the Mississippi, when that muddy water, which has a lot of colloidal clay in it, meets that highly salty ocean. The electrolytes in the ocean actually cause the precipitation of those clay particles, and you get the delta forming at the mouth of the river. This can be used industrially to separate soot, say, from a smokestack. Soot would pollute a city, and so if you say you have a coal powered electric plant and you've got coal smoke coming out of the smokestack, soot of course is going to dirty up the city. So what you can use is something called an electrostatic precipitator to cause the colloidal soot particles to coagulate and form larger particles and collect the soot before it leaves the smokestack. It's important to realize that colloids are not just solids in water. It can be a lot of different dispersing phases and dispersing mediums. A foam like shaving cream is a colloid. Solid foam like foam rubber is a colloid. An aerosol like fog or mist, or say something that sprays out of an aerosol can be a colloid. So there's lots of examples of colloids described below. So I'd suggest you study that blue table down below. Wrapping up, one identifying characteristic of a colloid is something called the Tyndall Effect. The Tyndall Effect is when you test your solution or colloid by passing a light beam through it. We see the flashlight passing through the solution because the light has wavelengths of, say, 400 to 700 nanometers, which are much larger than the water molecules that are much less than a nanometer in size. There is no interaction, and so the light passes through the water with no change. However, the colloidal particles have size that are similar to the wavelengths of the light, so you get some interactions there. And in fact, the light beam is scattered, and you can see the beam passing through the colloid. You also see this with headlights shining through fog. As you see on the left in the blue table, fog is a colloid. Headlights are a beam of light, and passing a beam of light through a colloid causes that beam of light to become visible because of the scattering of that light by the Tyndall effect. So if you pass a beam of light like a laser or a flashlight or a headlight through a mixture and see the Tyndall effect, you know it's not a true solution. It's in fact a colloid. Thank you everybody for your attention, and this concludes Chapter 11.